Very good morning to everyone. This is Shubhangi Rao and I am working as an assistant professor at MLR Institute of Technology. Today we are going to discuss about the topic capacitance. So let's start. This is the general arrangement for capacitance. Right. In general words, we can say it stores charges, right? But how exactly? What happens inside the capacitor? What is the arrangement? This we are going to discuss today in this session. So here you can clearly see in this diagram, this is conductor 1, this is conductor 2. In simple words, we can say this is first material, this is second material, okay. And here it is containing positive Q charges, okay, and it is containing negative Q charges. And if you notice, it is separated by a dielectric, right? And here you can see some field is established, right, when some supply is given. So this arrangement, this entire arrangement where two materials are there, or we can call it two conductors are there, and they are consisting equal and opposite charges, positive Q and negative Q charges, and they are separated by a dielectric. So this all arrangement is called capacitance, capacitor, right? So we will discuss the formula now. C is equals to, we can write Q upon V, charge upon voltage, and Q is equals to integration of d dot ds as per Gauss law. In place of d, we can write epsilon E, okay, and this is potential, and this can be written as minus integration of E dot dl. Now we put Q and V into this formula, and this becomes C is equals to integration of epsilon E ds divided by minus integration of E dot dl. We further simplify it, we rearrange it, and finally we write this formula for capacitor, right? So it becomes epsilon integration of E dot ds upon minus integration E dot dl. This is capacitance. So various arrangements of capacitance we can discuss. So first we will discuss about capacitance of parallel plate capacitor. Here in this arrangement, if you notice, we have two plates or two conductors, you can say again, but here it is in the form of plate. First plate is accumulating positive Q charges, second plate is consisting negative Q charges. The distance between these two plates is d, okay, and some dielectric is there which is filled between these two parallel plates, and also we are considering the plate area is A, right. Here again we will consider, to solve this problem, we will consider a small pill kind of structure, and we will see how we can develop the formula for capacitor. Here, because it is a surface, so surface charge density will be there, which is given by rho s is equals to charge per unit area, okay. So there are some points we will discuss. We already have discussed that area is A, it is separated by distance d. On plate 1 you can see positive charges, on plate 2 you can see negative Q charges which are distributed uniformly, okay. The distance between plate is assumed to be very small when it is compared to the dimension of the plate, means that d is much smaller than A, okay. Next we are going to apply Gauss law, and we are considering the small pill box shape structure, okay. So as per Gauss law, Xi is equals to Q is equals to rho s del s, okay. And if you notice in this diagram also, only the bottom face of the cylindrical Gaussian surface contributes towards the electric flux, this one, this portion, right. And we will see that the electric flux density on the bottom face of the Gaussian surface will be given by is d, and we can write Xi is equals to d del s, right. And this d del s is equals to rho del s can be written, and del s we can just avoid it, and we can get the formula D is equals to rho S. Now, if you have to see the direction, you can write negative AX as you see in the diagram. This is positive X, this will be negative S. So, we are talking about this. So, finally, when we try to write the unit vector, we can write D is equals to rho S minus AX. Okay. Now, electric field intensity on the bottom face of Gaussian surface will be given by E is equals to D upon epsilon, which can also be written as minus rho S upon epsilon, because D is equals to minus rho S AX. So, E can be written as minus rho upon epsilon AX. Okay. And we know that rho S is equals to Q by A, where Q is the charge and A is equals to surface area. So, charge per unit area. Now, we put the value of rho S into this formula and we get E is equals to minus Q upon epsilon A AX. This is electric field intensity. Now, we have to get the potential. So, potential is minus integration of the range is 1 to 2 or 2 to 1 we can write, because two different plates we have. So, the distance between them is D. So, for marking it we have written 2 to 1 E dot dl. Okay. So, now if we want to put limit we can just write 0 to D, and in place of E just now we have got this formula E is equals to minus Q upon epsilon AX. The same we can put in this potential formula. In place of E we will write minus Q upon epsilon AX, and dl can be written as dx AX because we are considering x axis. Now, this Q upon epsilon A can be considered outside because they are the constants, and integration will be with respect to dx. Okay. So, when we integrate we get x only, and when we put limit we get 0 to D, and ultimately we get V is equals to QD upon epsilon A. Now, this we need to put in the formula C is equals to Q by V, right, or directly by rearranging we can get it. Okay. So, when we get V is equals to QD upon epsilon A, this can be rearranged. So, if you write C is equals to Q by V, it becomes epsilon A upon D. QQ will get cancelled and finally we get epsilon A upon D. So, the capacitance of parallel plate capacitor will be given by epsilon A upon D. So, it depends on the, we can clearly see, it depends on the area of plates and the distance between the parallel plates. Next, we will consider coaxial capacitor. Here you can see we have a coaxial capacitor. This is inner capacitor. This is outer one. So, in place of parallel, we are taking in the form of cable. So, this is first one, this is second one. If we consider the radius for first one, the radius is A, for second one, the radius is B, and the length of this is L. Now, let us see. The space between the conductor will be filled with a homogeneous dielectric whose permittivity is epsilon. Okay. Again, we will assume that conductor 1 will be consisting of positive Q charges and second will carry negative Q charges and uniformly distributed over them. Now, when we apply Gauss law, we will obtain the electric field between the cylinders, and the formula for them is given by E is equals to Q upon 2 pi epsilon rho L A rho. As we already have the formula for E, we can put it into V. V is equals to minus integration of E dot dl, and because here we are considering radius A and B, so we will put the limit AB, and in place of E we will write Q upon 2 pi epsilon rho L, and in place of dl we will be writing d rho A rho. So, again when we further simplify it, Q upon 2 pi epsilon L will be considered outside as it is constant, and there will be only integration of 1 upon rho with respect to d rho. So, we will get ln rho, and when we put limit we get ln B by A, or it can also be written as ln B minus ln A. So, this is V. Now, from here we can obtain this formula. So, when we put it here in V value, this QQ will get cancelled, this 2 pi rho L epsilon L will come in numerator, and this is the final formula. So C capacitor for coaxial cable or coaxial capacitor value is 2 pi epsilon L upon ln B by A. Third arrangement is spherical capacitor. So two spheres are there, one inside another. The inner one is having A radius and it is consisting positive Q charges. The outer one is having radius B and it is consisting of negative charges. Okay. And between them some dielectric material is filled, homogeneous dielectric material is filled with permittivity epsilon. Again, when we apply Gauss law, we can find out the electric field of this kind of system. So we get the formula for electric field as Q upon 4 pi epsilon R square AR. Now again the next step is similar for every arrangement. Potential. We need to put the expression for E in the expression of potential. So we will put again, because the limit is we are considering radius, so we will put from B to A, and in place of E we will write Q upon 4 pi epsilon R square AR, and this dl can be considered as dr AR because we are considering it is radially outward, radius. So in place of dl we will take dr AR. Further simplifying again, Q upon 4 pi epsilon, it will be considered as constant, it is a constant, and then we will integrate 1 upon R square with respect to dr. When we simplify and put limit, we finally get Q upon 4 pi epsilon within bracket 1 upon A minus 1 upon B. And when we put this into this formula, C is equals to Q upon V, again Q will get cancelled and we will get 4 pi epsilon upon 1 upon A minus 1 upon B. So here we discussed about capacitor in general form, then we discussed about parallel plate capacitor, then we discussed about coaxial capacitor, and third we discussed about spherical capacitors. Few more special cases can be considered like two-wire line. They can also be solved by following the similar methods. So this was about capacitors. In case of any queries, please write to us. Thank you very much.